In this video, we will introduce our work, Point Query Quadtree for crowd counting, localization, and more. Crowd counting aims to predict the number of people given an input image. The main approach in crowd counting is to estimate the density map, where the count value is obtained by integrating the density map. Despite being effective, density map-based methods lack instance-level object information. In addition, these methods often require customized designs for specific crowd-related tasks, such as partial annotation learning. In contrast to previous methods, we formulate crowd counting as a decomposable point querying process. Given an image, we set some sparse points as queries. Sparse points are decomposed to new dense points when necessary, forming the point query quadtree. Then, counting can be achieved by querying those input points. Such a querying process yields an intuitive, universal modeling of crowd as both the input and output are interpretable and steerable. By simply adjusting the inputs, this formulation is applicable to a number of crowd-related tasks, such as fully supervised crowd counting and localization, partial annotation learning, and point annotation refinement. Here is an overview of our point query transformer, dubbed PET. We first use a CNN backbone to extract the image representation. Next, a transformer encoder with progressive rectangle window attention is applied to encode context. The idea is that the transformer encoder first inspects a sufficiently large region and then focuses on a small one. Subsequently, the quadtree splitter receives sparse querying points and encoded features as input, outputting a point query quadtree. The quadtree is dynamically generated based on the input image, under the guidance of the split map. The transformer decoder then decodes the point queries in parallel, where attention is computed within a local window. These point queries are finally passed through a prediction head to obtain crowd predictions. We optimize the model using bipartite matching between the predictions and ground truth points. In addition, we also supervise the quadtree splitter to discriminate dense and sparse regions. We evaluate our approach on a number of crowd-related tasks, including fully supervised crowd counting and localization, partial annotation learning, and point annotation refinement. Our approach achieves state-of-the-art results on existing crowd counting datasets and outperforms previous methods by a considerable margin in crowd localization task. Without bells and whistles, our approach also performs favorably against existing methods in partial annotation learning, in which only a partial region of each image is annotated. Another interesting application of PET is point annotation refinement. We observe that PET can distinguish noisy annotations and calibrate these points to the center of the head. This could be useful for tackling annotation noise. Here we justify the design of our approach. As shown in the table, solely using sparse or dense point queries does not achieve satisfactory results. Comparatively, by adopting the point query quadtree, we obtain notable improvements. This validates the effectiveness of the point query quadtree. The learning process of the quadtree splitter is also shown in the figure, where red regions denote dense regions. We can observe that the quadtree learns to discriminate sparse and dense regions in a few training epochs. Now we analyze the role of encoder and decoder. Interestingly, the attention map of the encoder and decoder seems similar. They both capture similar crowd information within a rectangle window. This may attribute to the single-class nature of the crowd, because the model only needs to distinguish human heads. In conclusion, we show that decomposable point querying can be a universal crowd modeling idea. And our approach exhibits generality in several crowd-related tasks. Thanks for watching.